AJ and Paul are here from Burke, and I'm not sure if anyone else has joined them, but the importance, and I sort of mentioned this during my report, is we want to make sure that how it was modeled when the Corps built this still holds true today. So the 200-year rain event is whatever it is. It's 597 or it's 600. And that's why we sort of held off with the US gauges to make sure that if we have new data today, it fits with our correct warning system. And so I have not seen this presentation. So everything that AJ and Paul bring for this, it will be new to me, but I'm looking forward to it. The second part of it, the most important, probably one of the more important parts is this is one of the components for them not only to certify the levy, but also a component or a piece of the pie to get the Lomar and Gary. So the last component that I see that we're responsible for, or that we decided to be responsible for, is the borings in the levy. And that is still in the 408 process of the Corps, but we won't argue at that point. I'll bring on AJ, there he is, and Paul, and I'm not sure who else he's got. So I'll let them have it. And
gentlemen, state your name and address, please, and rock and roll.
Yes, thank you, Chairman Baker. Thank you, Mr. Repay and board members. This is AJ Fricke with Christopher Burke Engineering, 111 Monument Circle, Suite 3500, Indianapolis, Indiana. I have with me Paul Dawley from our staff. And also,
go
ahead,
I don't know if I have. Okay. I'm Paul Dawley. I'm also with Christopher Burke Engineering in Indianapolis at 111 Monument Circle, Suite 3500, Indianapolis.
We also have two other staff members online, Sivash Bake and Peggy Shepard, also of the same office. We have a presentation to share this evening. Paul, you are operating that. Do you have the ability to start sharing your screen, or do
I do not. Can I have that granted to me, please?
Yeah.
the lights off or no? Can you see it?
I don't know what I'm seeing.
Oh, I'm gonna ask you, can you see the TV okay now, or do you want me to turn the lights down? Because you're gonna see something.
Yeah. Oh, perfect. Okay, thank you.
You said you have two other staff on the call?
Yes. Yeah, we have Mr. Sivash Bake and Miss Peggy Shepard on the call.
Hello.
There you go.
Sivash, if you want to say hi too.
I'm trying to, but yes, hello everyone. It's a pleasure to be here, and thank you for listening to us today.
Okay, great.
Looks like. Can people see my screen?
Yes.
Okay, great.
All right. Great. We'll go ahead and get started here. I'm going to start with a few slides, and then I'm going to turn it over to Paul, who did a lot of the modeling on this project. So Paul, can you advance to the next slide on our presentation? All right. Mr. Repay gave a great introduction to why we're doing this, our 2D hydraulic modeling of the Little Calumet River. And I'd like to outline some of the topics that we're going to be covering this evening. First, we'd like to cover the project purpose and scope, tell you a little bit more about what we're doing and why we are doing it. Also discuss some of the challenges we've encountered on the project. Also discuss why we chose to do 2D modeling. As Mr. Repay mentioned, it's been a very long time since this entire system has been modeled or checked. Modeling capabilities have certainly advanced since that last occurred. So we feel like we're bringing the highest level of technology and modeling sophistication to this project. After I get through a few of those slides, I'm going to turn it over to Paul. He's going to talk about the 2D modeling itself, what we did there, and the findings and results of those as well. And then we'll end with some next steps. And I'm sure there'll be questions at the end, and we'll be glad to address those. Next slide, please. So the purpose of our project is to estimate the water surface elevations along Little Calumet River during various flood events using updated data and two-dimensional or 2D modeling. So we're going to look at a range of different events that could occur on the river, see what water surface elevations those produce, and then based on that, we'll evaluate the levee system freeboard or height. And basically what we're doing is comparing those water surface elevations to the top or crest of the levee to make sure that those flood events are contained within the levee. Our scope of work includes several items, but three main things here that I want to point out. The first was collecting and processing survey data for 30 plus miles of levee. That is done. We previously presented a presentation on that. So we have the levee crest elevations throughout the system. We also did some supplemental surveying to support our hydraulic analysis as well. We are in the process of wrapping up our detailed 2D model of Little Calumet River. That's really the heart of what we're doing. And then again, performing those freeboard evaluations to compare the water surface elevations to the levee crest elevations. So why is this important? I think Chairman Baker said it best in the beginning, right? This is a $275 million man-made flood control project. We want to make sure that the events of September 2008 don't happen again. So we know that the levee system protects many assets in the community along the river. So we want to identify any potential problems that may be corrected based on the data that we find out. We also want to collect data that may be leveraged in the future to apply for a letter of map revision, specifically for the east reach of the system. That would be east of Klein Avenue in Gary, or a continuation of previous letter of map revisions for the west reach. Already has those LOMARs from FEMA, but there may come a day where those need to be reaccredited or recertified. And that's important because that pertains to the flood insurance rate maps. There's a few key questions that we want to answer with our modeling, and we'll go over tonight at the very end. The first question is, would the levees contain the river if the 2008 flood happened again? I think that's a very important question. The second is the levee tall enough to meet FEMA requirements? Because that pertains to the letters of map revision. And then number three, what are the impacts of the proposed Kennedy Avenue bridge work on the river hydraulics? And then finally, in the future, what are the impacts of other projects? We don't know what those might be yet, but we're confident that this model can be used in the future to evaluate future projects. Next slide, please. This graphic shows a map of the levee system. We wanted to present this just to make sure that we're all on the same page. Our study limits include the entirety of the system from the Indiana-Illinois state line to the west, all the way to the confluence of Little Calumet River and Deep River to the east near the interchange of Interstate 70 and I-8094. So we're talking about all the communities in between there: Munster, Hammond, Highland, Griffith, and Gary. Our two main inputs into the model are Hart Ditch, which flows from the south, and then of course Deep River on the east too is an important component of our model, in addition to the Little Calumet River. So I just want to make sure that everyone understands our study extents here and the levee limits that you'll be seeing throughout our presentation, which are shown in various colors on this graphic. So now I'm going to turn it over to Paul, who's going to talk a little bit more about our modeling efforts.
Great, thanks, AJ. Like he said, I'm going to walk through a little bit about what went into this modeling, as well as show some results for everyone. So just to give a quick overview about what 2D modeling is, 2D hydraulic modeling is, it is a way of modeling that expands upon the traditional one-dimensional hydraulic model, which is done with cross sections, as you see here. That's what these green lines are, by allowing for computations at many, many, many more places. So in the traditional one-dimensional model, you have maybe a few dozen cross sections that define the topography, and that influences the flow that goes through it. And generally the flow is assumed to be in one direction. With the two-dimensional model, you see all of these black polygons and lines here. Each of those black lines is what's called a cell edge. That's essentially a cross section. So just in comparison between these two, you can see that there's a much higher density of computational cross sections to be able to compute where flow goes, which is especially important in a complex system like this, where flow is splitting multiple directions. coming from Hart into Little Calumet. So to go a little bit more into how the two-dimensional cells work for these computations, we'll just zoom in on this area here. I have a cell highlighted in pink. Basically, the cell is like a cube, if you will, with each of the edges showing the cross-sectional terrain based on the topography. And then it, based on that, creates a volume elevation relationship. So if there's a certain volume of water within the cell, then it will show a certain water surface elevation, again, based on the underlying topography. So just to walk through a little bit of what AJ was describing as far as how this system works, especially as it relates to how we modeled it. Here we have the primary inflow to the Little Calumet River, which comes from Hart Ditch. It flows north until it reaches the confluence with the Little Calumet River here, which then splits the flow into a east and west reach. In our model, the west reach flows to the Illinois state line over to the west. And to the east, it flows down to the confluence with Deep River, which we included both the inflow and outflow from a portion of Deep River here in order to account for and capture the backwater effects that it has on the Little Calumet River, which can affect the water surface elevations along the Little Cal. So here I'm going to show a graphic animation of the 100-year storm event developing in the west and east reaches. I want to call attention to along the east reach here, you'll see some of these storage areas as the 100-year storm develops, filling in and taking some of that water that had been flowing as it gets out of the channel and into the overbanks. Here is a interesting, yeah, there you go. The ooze, the flow always gets the ooze. This is the confluence with Hart Ditch coming from the south here, and then the split east and west into the Little Cal. So you can see that not only does it split at the channel here, but we also have a little bit of overflow in the overbanks here. I know I've talked to Mr. Repay about this overflow channel to the east here, which you can see a somewhat substantial amount of flow coming through this way.
So I have a quick question, if I may.
Yep.
Can you determine the volume of water? What percentage of it coming down Hart's Ditch goes west versus going east?
Yep. Yes. Yes, we can. I can talk a little bit about that a bit later.
Okay.
But that is something that was important for us as one in calibrating the model. So calibrating to observe data from gauges on the along Little Cal and Hart, but also comparing to other conditions like FEMA.
Thank you.
I just want to make a comment.
Yep.
Dan, this is the reason that you said that if you unplug the quarry at in Thornton, all the water is going to the east from here. This is why the rain gauge that does not support the water here at this. It doesn't go down here because of this right here.
And I don't know if Paul has put that in his model or not, whether they take into consideration the quarry. But when the quarry reaches 9, I believe, everything from this confluence really accelerates. And that's why when it hits a 597 mark or ish at the North Cod Bridge, it will stay at that level because the water is going so hard or fast to the west and doesn't necessarily impact it all the way to Indianapolis Boulevard or Kennedy. So, and just for the record, if you look at this model, as it was left to us when I first started, the only option for this water to flow was the dark blue when it hit that T. And in 2007, it blew out that segment of the levee. 2008, they secured it, but that is the backup or the ponding, I guess, what they have. I'm sorry, Paul, I'll stop being a
Oh,
hydraulic.
that's good. That's great to know. This is an interesting context. To answer your question about whether or not the quarry is included in the model, it is not. So that's actually maybe a discussion that we should
Paul,
have
it
as
is.
well to follow up on that.
I'm
Is
sorry,
it?
Paul, just to point out that the hydrograph that we are using on the state line, Illinois state line, come
Sure.
from or modeling that does include the that quarry. Just a explanation. Go ahead.
Yeah, thank you, Siavash, for that clarification. Okay, let's look at some other areas of
Right.
interest.
Yes.
Okay.
So here we have the flow control structure. This is just west of that Hart and Locale confluence. We saw we have Northcott is just a little bit downstream of this. This shows how the control structure restricts the flow going to the west. You can see that some of the flow speeds up as it goes through the restriction. We'll see that at other restrictions as well, like bridges, but you can see how it's restricting the flow to the west. And then here we'll see another animation of the 100-year storm developing. This is right by Klein Avenue. Yep. And we can see the storage areas around Klein filling in once the water level hits a certain elevation. And so there's actually quite a few areas like this along the east reach, whether it just be either wide floodplain in the overbanks or storage areas like this. So now to take a look at the impact of Deep River on Little Cal, the East Branch. We have Deep River down here on the east side, and then Little Cal coming from the west, flowing to the east. We'll see that early on in the 100-year storm, the Deep River actually backflows up a small portion of Little Cal. So I'll just start it here so we can see this. So we see flow coming right from deep to the west and flowing into this area here, while flow from Little Cal is coming from west to east, and they're kind of meeting in the middle here. This is caused by Deep River having a higher water surface elevation than what Little Calumet is having. And so the water's flowing partially past the path of least resistance, and it's flowing up Little Cal and into this area. We'll see that as the storm develops, so this is 48 hours in the model, this is 48 hours after what I just showed you. The flow direction of Little Cal down by Deep actually flips, and Little Cal flows out into Deep and then out of the model. And that's due to the elevation falling in Deep River and kind of all of that water that was backed up in Little Cal, then exiting the model into Deep. And out.
If I get flooded.
So just to talk a little bit about the what went into the model development here, we calibrated our model to the observed data from a variety of gauges that are on the east and west reach of Little Cal. This is for the late April, early May 2019 storm event, which seems to equate to approximately the 5-year event. And we calibrate to make sure that our model is properly reflecting the observed conditions. Some of the parameters that we analyze the sensitivity of to see how they affect the performance and how they help match the observed condition include pumps for interior drainage, the roughness of the land cover, analyzing significant topography features and making sure that they are included within our computational mesh, playing with the boundary conditions like Siavash had mentioned earlier. We had stage hydrographs set as the boundary conditions based on data from the Corps of Engineers model. And then some other input parameters were tested as well. We also simulated some other events, and we'll continue to expand out which events we've simulated as we move forward. But some of the ones that we have currently done is an analysis of the 100-year storm event, which is what I had showed some of the animations from. The proposed Kennedy Avenue bridge, we've evaluated that at the 100-year storm event as well. And then we also took a look at the September 2008 flood conditions, assuming the current existing levee system topography is in place. And AJ will answer some of those core considerations and questions in a second here. As far as project challenges go, this is a very large and highly complex model. We had about 16 miles of river and 28 miles of levee within the model, as well as 34 bridges and culverts and 82,000 computational cells. So again, think about those cells have a bunch of faces that are basically like cross sections. So compare, maybe a few hundred cross sections in a one-dimensional model to 82,000 plus in the two-dimensional model. We had a lot of data collection that went into this, including developing the two-dimensional mesh to represent the real topography based on some survey data, data that was present in the core model. Also putting in for a lot of the bridges and culverts based on either the core model or existing plans. There's obviously some complexity of the flow splitting at Hart Ditch. I showed that animation earlier, but it's a very unique system there. I think the two-dimensional modeling helps capture some of the complexity there better than what the one-dimensional modeling can do. A challenge that we ran into is that there are actually only 2 stream gauges that monitor discharge. So there's one at Homan, which is on the west reach of Little Cal, and then there's one at Hart Ditch. Unfortunately, there aren't any gauges that monitor discharge on the east branch, so that made calibration a bit of a challenge. Another thing to consider, we had 26 pump stations contributing flow to the river from interior drainage, and we had to make some assumptions as far as the magnitude and timing of how those contribute. Also, as we saw, the significant backwater impacts from Deep River make this system very unique and make it important to include Deep River in the model itself. And we walk through looking at the impact of some of the storage areas and volume in the East Reach. We also are trying to build this model for the future for meeting certain FEMA requirements. So there's also consideration given to meeting those as well. So I'm going to hand it back to AJ to go through some of those core questions. Oh, and there's a little bonus for you. Model takes 10 to 12 hours. 10 to 12 hours to run on a good fast computer. So just to give you a sense of perspective on how long it takes. We'd run them overnight a lot.
All right. Thanks, Paul. Appreciate that great overview of our project. So I want to get back to answering some of the questions we posed at the beginning of our presentation. And question number 1 was, would the levees contain the river if the 2008 flood happened again? So that answer is yes. The flood should be contained within the levees, but do have a little bit of a caveat here.
Fine print.
Yeah, fine print down at the bottom. That is subject to road closures being properly installed. And when we look at our model, there's 3 in particular that stick out. Northcott, Kennedy, and Grant are probably the most consequential in terms of needing to be activated first. We did also note that the past projects that the Basin Commission has taken to eliminate closures at 35th Street and Georgia Street and Gary have definitely had a positive impact, because those would be consequential in a flood equal in magnitude to 2008. So flood like that happen again, you're not going to have a manually operated closure at those locations. Also, we want to make sure that pump stations are operating properly to discharge interior runoff, and that backflow prevention is functioning properly to help prevent interior flooding. So there may be a riverine flooding event that's going on the river, but on the protected side of the levee, it might be raining. It's important to make sure that that runoff, that water gets discharged safely to the river. And finally, no major blockage at bridges and culverts. That's really important to keep all the bridge openings, culvert openings free and clear so it can pass the floodwaters. All right, our next question was, is the levee tall enough to meet FEMA requirements? And I'll focus on this graphic here and explain what freeboard exactly means. So when we're talking about freeboard, that is the difference in elevation between the flood elevation and the levee crest. So it's essentially that top portion of the levee that's kind of a factor of safety, gives you a little bit of extra height. We typically want to see that in the 3.5 to 4.5 foot range to meet FEMA requirements. If you go look at the Code of Federal Regulations, the freeboard is somewhere in that range above the 100-year flood elevation. So the answer to this question is that based on our model results, that most of the system meets freeboard requirements for FEMA, but there are a few clarifications yet again. Did want to point out that the 100-year flood, the regulatory flood, it is contained within the levees, and there is freeboard. So that means that the water's not getting up to the levee crest. It's not lapping at the top. There's distance between that flood elevation and the levee crest. Although there is some freeboard, there are a few spots where the FEMA freeboard requirement isn't strictly met. And when we really boil down to it, those FEMA requirements are really only consequential if a LOMAR is being pursued. So we know that we have a levee system that is built to withstand a certain level of flooding. It wasn't necessarily designed to meet all the FEMA requirements, but we can safely say that it does have freeboard over the 100-year flood along its entire length. Next slide, please. One of our other questions was, what are the impacts of the proposed Kennedy Avenue bridge work? So just as a quick overview here, our understanding of that project is that the bridge is going to be replaced, and that will eliminate the closures on both sides that would need to be implemented if floodwaters were anticipated. So the answer to that is what we found in our hydraulic model was that the new bridge really doesn't have a huge impact on the 100-year flood event in terms of the water surface elevation. We're still running the 200-year event to see what that looks like. We know that there's perhaps a larger opening there, fewer or no piers, so there's probably is some benefit. But the main thing is that there's a significant reduction of flood risk by eliminating those manually operated road closures. So just like we saw with 35th Street and Georgia Street and Gary, how if the 2008 flood would happen to come again, that those are good to go, right? Because there's no temporary closures there. That's going to be a huge benefit to everyone if that's the same situation here at Kennedy. So one more slide here before we wrap up and open it up to questions here. Just want to review what is left here as the next steps. On our current assignment with you, we want to, of course, incorporate any feedback that we receive from you during the meeting this evening or otherwise. And then we will make some final refinements to the model inputs and fine-tune things, run some of those additional storm events that we haven't run yet, finalize our calculations on the levee height or freeboard, and then we'll be delivering a final documentation report to you that summarizes all of our findings. We did identify a few things for potential future improvements that may be beyond this project. If we want to improve this model in the future, we would want to obtain some additional improved surveying data or bathymetry, and that means what are the elevations of the river below the water surface, right? What lies beneath? We know that you do dredging projects, and that is very beneficial to keeping the river conveyance what it needs to be. But we know that rivers are dynamic systems, things change over time, and it's good to keep on top of what the river is. And then also full integration of the interior drainage. Paul mentioned some pump stations. There's 26 throughout the system, and the timing of those, when they turn on, when they turn off, that can have an impact on how things work along the river. So that just is another layer of complexity. We've made our best assumptions at this point, but that would be a way that the model could be further refined. And then finally, improve the calibration if more data becomes available, specifically the discharge. As Paul mentioned, we don't have anything to calibrate to east of Hart Ditch in terms of discharge. There are gauges that report stage, but they don't report discharge. So if we had that data available, that would also help us to improve the calibration on the model. So we've reached the end of the presentation here. That was our crash course in the model here, and we would be glad to answer any questions that you may have.
Very good.
Wow, that's impressive.
That was outstanding. So appreciate that, folks. As far as additional modeling requests, I mean, how are we doing the maintenance of this and the manage it? One of the discussions that we've had here over the last, 6 months or so had to do with the event where 9 inches of rain fell, along Lake Michigan shoreline. And what would happen if that 9 inches of rain fell directly on the Borman Expressway, and what impact that would have? Is that, how are you handling it from a business perspective? How about that? If we give you that request.
Yeah, Chairman Baker, thank you for that question. That's a good question. And as I mentioned earlier in the presentation, we definitely want this model to be useful to you moving forward to evaluate new projects or new situations like that. That specific situation, we'd probably have to give some thought to that, but we might have to augment that model a little bit to develop a discharge that would be associated with that and then plug that into the model. I'll maybe ask Paul and Sivash and Peggy if they have any thoughts too, what that might entail.
Yeah, I could just explain that the model that we have right now, Chairman, is working based on flow that is running through the stream. There are other models where you have rain that comes in, hydrologic models that have, and they play into the interior drainage. There's also other advances recently that they call rain on mesh, which means rain comes down on the watershed and basically the hydraulics work together. It knows how much rain comes outside. It connected, and AJ, I think, mentioned that integration of interior drainage and modeling with the channel modeling. Right now, we don't have that capability. We do have the capability to do it, but we don't have it in our scope or feel they're, really complex, more complex than what we have done. It can be done. And there are ways to also estimate what you're mentioning, but like AJ said, probably we have to do some additional hydrologic model to evaluate that. Also, just for the updated model we have, as you remember, we did the deep river model with all those what if situations. And this model that we have just developed is going to be connected to that other model so that you can also ask more what if question. But it's absolutely important that you probably put some sort of a allowance per year to review the model, update it if needed as go forward. The bridge changes, that something goes on right now. For instance, we have a existing condition of Kennedy Avenue Bridge in the model. As thing changes, we need to change that base model to that condition. So I hear what you're saying, and I agree with that. Many times we develop stuff and sits there and it becomes, outdated. And I think some sort of maintenance is possible. We're more than glad to help if that's a desire.
So for that maintenance, if you look at it from the chair I'm sitting in, that is going to be request that comes from Christopher Burke from the office here. and then you're just gonna do a proposal of what it's gonna take to upgrade the model or to incorporate it into the model?
If that's the desire, we should be more than glad to do that. Yes, sir.
Thank you. Any questions for these gentlemen?
I have a couple questions.
Lay them on.
Hey, Mr. Frick, did I pronounce your name right?
Fricky,
Fricky.
yes.
I just wanted to know, two things. One, a project like this or model, how long will it take to complete? And second, what is your history with FEMA as far as approving any kind of a project like this for this particular area?
Yeah, yes, sir. Great question. So we do have some work to do to wrap things up. We're anticipating maybe about 90 days to finish everything up and put the finishing touches on what we're currently doing. In terms of experience on this, we're certainly experienced with letter map revision project, and especially along Little Calumet River with the letter map revision east or west of Klein Avenue, rather. The 2D modeling is a little bit new in the FEMA world. We're still getting used to that. I think the regulators are still getting used to that, but we do have some ideas about how that might work going forward. In fact, we talked about that a little bit today, and that there's ultimately a long range goal of accrediting the levees east of Klein Avenue and Gary. And one initial step might be to actually submit this model or some kind of derivative thereof as a first step to kind of reset the hydraulics along the stream. And then we would submit a letter of map revision later to accredit the levees after the hydraulics are reset. So hopefully that answers your question. If it doesn't, I might call on a couple of my colleagues here to add some additional clarifications.
The question I asked specifically is that how long will this project take? That's what I wanted to know.
Yeah.
Once it
Complete
started.
the current assignment?
Yeah.
Yeah, we anticipate about 90 days to finish this current
No,
assignment.
AJ, I think the question is typically how long it takes to run this model, and I will tell you that based on experience that we have done, this model is so complicated. It's probably 1.5 to 2 years of development. I don't remember exactly when we were authorized to do that, but we had to obtain some data, in particular some bridge data and some topography data, and so it takes time. That's a patience, and I think even the type of a additional model, if you will, or improve or going to a different rain-based type of a thing is even takes longer. So it is a long process. It's not easy by any means.
And what can we do to help you make this project come faster than 2 years?
Well, of course, hopefully we are completed. We'll complete this sooner, and within the next one assignment, if there is one, we'll put every effort we can to make it faster. No question about that.
Okay, thank you.
Got a question. In the presentation, you had mentioned there you used 2 stream gauges, and you suggested that additional stream gauges would be beneficial. Are you going to recommend locations for those and what we should think about doing?
Yes.
Our gauges, what he's talking about is there's several different types of gauges. So we already have height gauges, and that's what we concern us with. I think that's a good question is to him, where would you like to put the discharge? Because it would just be an add-on to our USGS contract to add that discharge component.
So
and I'm sure
that would be a
tell us.
component to the USGS gauge?
Yeah, the gauges that we have all throughout the system mostly are just height gauges. The discharge, there's one at the dam in Hobart. He's mentioned the one on Holman. There's one on Hard Stitch, but he's saying, like, I guess to Siavash or to AJ, whichever, would you like to see it at Grant? Would you like to see it at Burr? If you could give us those suggestions, we can make that amendment to our USGS current agreement that we have with them.
Sure, Dan. We'll definitely see where it is possible. We are trying to, when you get closer to the deep river, you're under influence of deep river too much, and so in a way that determines what the discharge is, but it could be interference. So we probably go a little bit further west, but we consult among ourselves, and it could very well be near Burr or Grant rather than further east.
Are we modeling the Deep River as well? We did already.
Yeah, we have already done
Yeah.
that in the unsteady state model, not the 2D, but we did that in the also a complex model.
And are we suggesting, obviously, to incorporate that into the whole big picture? See,
Yes, it is already connected together.
It is.
Peggy, if you want to add
Yeah.
anything.
A section was pulled out of that 1D Deep River, and then, or data from that was pulled into this model. So it is in the sense that it's got provided a boundary condition, but it isn't physically the model all running together, which it can be.
It can be, and I will just add this additional explanation. It is possible to connect many models together, but the timing, the running time will become, that's what, so oftentimes you run one model, you get some output from it, and then you consider that in the other model. So there's a connection, but it's not, push some button and everything runs together, not at least at the time with the computers we have.
Sivash, how much for that button?
I know you always future looking. We like to do the same thing as well. I don't know how that answer. Chairman Craig. Earlier comment, I just want to don't take the time, but I think many of you know we do have good experience with the Lomars along the string. In fact, I think all the Lomars to the west of Klein we were involved with, and we got those Lomars. So hopefully we know something about Lomars. Now the 2D model is a bit more complicated, but I'm sure we will be able to accomplish what we want.
Good.
Any other questions for these folks?
Yeah, I'd just like to say one more question. I want to thank you for an excellent report. Thank you. We appreciate that.
Thank you. Appreciate the opportunity.
So I have a question with regards, Christopher Burke has done significant amount of work along the Hart Ditch as we continue to try to fortify that, tributary, for lack of another term. Do you see any benefit for modeling that particular part of the system?
Yes, definitely, Chairman. In fact, we have, as a current model, it makes some assumptions in terms of the flow that's coming in. We have a gauge. It's at Hart Ditch, but it's also sometimes there are high flows influenced by the downstream portion of that. So definitely there will be benefit, and I think that may be another future type of endeavor, which we more than glad to suggest as well as we finish.
One of the things as far as the forecasting thing, and I'm sure Dan's communicated this to you on more than one occasion, is that as sections or southern portions of the watershed continue to get developed and more cornfields become hard surfaces, for lack of a better term, and taking the information that comes from the municipalities as it relates to what they're trying to do in some of these locations and its impact on the system, to be able to turn that around in a timely manner will help economic development, as well as making sure that the system itself can be able to handle those types of modifications.
Yes, sir.
Any other questions? Outstanding. Thank you very much.
Thank you.
It's been a pleasure.